Hello everyone, welcome to course study on solid mechanics. In today's lecture, we are going to discuss or we are going to derive the Euler's formula because the strength of the column and the types of end condition that we have already discussed in the previous lecture or in the last lecture. Okay, so in today's lecture, we are going to derive the Euler's formula. So to derive the Euler's formula, we are going to consider both ends of the column as a hinged one to derive the Euler's formula, and as per the syllabus we are going to consider both ends as a hinged one. Okay, therefore we consider from the figure, we are going to concentrate on figure as well as on the theory. Okay, so consider a column AB of length L with the uniform cross sectional area as shown in the figure. Okay, so from the figure A we have a column AB. Okay, this is the x direction and along this it is the y direction. Okay, and that particular column has a length L. Okay, and A is hinged one whereas end B is also hinged one. Okay, so we are going to find out, we are going to derive Euler's formula for the both end hinge condition. Okay, and this particular column is subjected to external load P here. Okay, therefore let P is equal to crippling load. All of you know that what is crippling load. It is a load at which the column just tends to buckle laterally. It is a load at which the column tends to buckle laterally. Okay, therefore as it buckles laterally, y will be the lateral displacement at a distance of x from the support A. Okay, y will be the lateral displacement at a distance of x from support A, and that is shown in the figure B. Okay, so as we go on increasing the load P, the lateral deflection will take place. Okay, and that lateral deflection is shown in this particular figure, that is in terms of y. Okay, and that y, it is at a distance of x from support A. So you remember this particular one, it is at a distance of x from support A. Okay, therefore the moment due to the load P at a distance of x from support A can be given by m is equal to minus P into y. The moment due to the load P at a distance of x from support A can be given by m is equal to minus P into y. We have minus sign because as per the sign convention which we have discussed in the previous lecture, we have the minus sign. Okay, because it is a sign which we have considered for the bending moment. Okay, therefore we have the minus sign and minus py. Okay, therefore this is the value of pm, this is the value of moment. Okay, in terms of force and the lateral displacement. The bending moment or the elastic curve equation at any point is given by ei into d square y by dx square. So this is the new concept for you. Okay, the bending moment or the elastic curve equation. Why it is elastic curve equation? Because due to the application of external load P, that particular column will bend into the elastic curve. This is the elastic curve. Okay, therefore the equation of elastic curve can be given by ei into d square y by dx square. So this particular value will work as a moment. This particular value will work as a moment. Okay, so if you put this particular value of moment in this particular equation, we have ei into d square y by dx square, which is equal to minus py, which is equal to minus py. Okay, so after rearranging this equation, we have this particular equation, ei d square y by dx square plus py, which is equal to 0 after rearranging the equation. Okay, now we will divide the above equation by ei. Therefore we will have the following equation, d square y by dx square plus p upon ei into y, which is equal to 0. Okay, and this equation we have obtained after dividing ei to this particular equation. Okay, therefore this equation is known as a second order homogeneous linear differential equation with y as a function of x. So remember that whatever the equation we have right now, this is a second order homogeneous linear differential equation where y is a function of x. So the value of y and x are related to each other. Okay, therefore the solution of this particular second order linear differential equation can be given by y is equal to c1 cos of into bracket x under root of p upon ei bracket completed plus c2 sine of x into under root of p upon ei. Okay, so remember that this equation, it is a solution of this particular equation. Okay, where c1 and c2 are the constants and can be evaluated by the end condition of the column. Remember that in this particular equation c1 and c2 are the constant value, and that can be found out by using the end condition of the column. Okay, therefore at a the deflection is 0. If you observe the diagram carefully, at end a this one deflection is 0. Okay, so at end a deflection is 0, therefore we can say that at x equal to 0, because x starts along this direction. See here, this is the x, this is the x. Okay, so at a x is also 0, at a x is also 0, therefore at x equal to 0 y is equal to 0. So what does it mean? You just remember this particular concept. At x is equal to 0 y is equal to 0, it means that the deflection is 0 at point A. You just remember this particular thing. The deflection y is 0 at point A. Okay, so if you put the value of x equal to 0 and y is equal to 0 in this particular equation, we will have c1 equal to 0. We will have c1 equal to 0, because if you put y is equal to 0 in this particular equation, if you put x equal to 0 here, if you put x equal to 0 here, so sine of 0 it will become 0, but cos of 0 will become 1. The cos of 0 will become 1. Therefore this equation will give you the value of c1, and that is equal to 0. Okay, now we will move to the second end condition. At end b the deflection is also 0. At end b the deflection is also 0. See here, but at end b x is equal to l, this x is l. Okay, and the value of y is also 0. You remember that at end b y is 0, deflection is 0, but x is equal to l. Okay, so again you have to put these end condition into this particular equation. Okay, so whatever the answer we will get, it is 0 is equal to c2 sine of l under root of p upon ei. c2 sine of l under root of p upon ei. Okay, so from this equation you will have two values. The first one is c2 is equal to 0, or sine into l under root of p upon ei is equal to 0. We will have two values, c2 equal to 0 and sine of this particular term will equal to 0. Okay, but c1 is 0. We have c1 is equal to 0. See here, we have c1 is equal to 0, so c2 will not be 0. As we have c1 equal to 0, c2 will not be 0, because if c1 and c2 both are 0, the column will not be in the bend configuration. If c1 and c2 both are 0, if we consider both as a 0, then the column will not be in the bend configuration. Okay, so we cannot consider c2 as a 0. We cannot consider c2 as a 0. Therefore we are going to consider this particular equation only. We are going to consider this particular equation only. Okay, so if I concentrate on this particular equation, the solution of this equation can be given by, we have this equation. Okay, so the solution for this equation is l under root of p upon ei is equal to n pi. Remember that whatever the answer we will have, it is a solution of this equation, which is equal to n pi, where n equal to 1 2 3 4 etc etc etc. Okay, therefore if we have to consider it for a standard configuration, standard deflection curve, then we must take n is equal to 1. we must take n is equal to 1. Therefore, considering the first or least practical value, we have L under root of P upon EI is equal to pi, because here it is we have considered n is equal to 1. If we consider n is equal to 1, then and then only we will have this particular deflection curve. Then and then only we will have the standard deflection curve. Otherwise, the curve will be different. Okay. Therefore, we have this particular equation L under root of P upon EI is equal to pi. Okay. The value selected above is so called as a fundamental mode value, and it is the lowest critical load producing the single bow condition. So as discussed earlier, it is known as a fundamental mode value. Okay. And it is the lowest critical load which will produce the single bow condition, because single bow condition, it is considered as an ideal condition. This type of deflection curve is a ideal deflection curve, and we have to compare it with respect to this one. Okay. And this particular curve you will get when n is equal to 1. When n is equal to 1, then and then only you will get this particular curve. Okay. Therefore, after rearranging this above equation, we have under root of P upon EI is equal to pi upon L. Under root of P upon EI, which is equal to pi upon L. Okay. So from this equation, we are going to find out the value of P, which is also known as a critical load, because we have considered P as a crippling load, and all of you know that crippling load can be denoted by PCR. Okay. So we will have P is equal to PCR is equal to pi square EI upon L square. Okay. Where I is nothing but it is the value of minimum moment of inertia. Okay. Out of the x-x axis or y-y axis. So we are going to consider minimum moment of inertia, because about that axis the deflection will the buckling will occur. About the minimum moment of inertia, okay, the deflection or the buckling will take place. Therefore, we are going to consider I minimum value. Okay. So always take minimum value of I. So it is already discussed. Okay. Now what will happen if I consider n is equal to 2? In this particular equation, we have considered n is equal to 1. But what will happen if I consider n is equal to 2? We will have this equation. If I consider n is equal to 2, then it will become in this manner. L under root of P upon EI equal to 2 pi. Okay. But if I consider n is equal to 2, our deflection curve will be in this manner. See here. It will be in this manner. And that is not our standard case. Okay. So for the standard case, our value of n must be equal to 1. Okay. Therefore, as shown in figure, n is equal to 2 produces buckling in 2 half waves. It produces the buckling in 2 half waves. Whereas if I consider n is equal to 3, then it produces buckling in 3 half waves. Okay. That's why we have to compare it with the standard condition, and that standard condition can be achieved when if we put n is equal to 1. Okay. So this is all about the Euler's formula. So the standard Euler's formula can be given by P is equal to, or P critical is equal to pi square EI upon L square. Everyone has to remember this particular formula. Okay. In the next lecture, we are going to discuss the effective length concept in detail. Okay. So we will stop here. Thank you.